Hello, everyone. Yeah. Yes, Maria, I think you can go ahead.
Gopal, can you introduce the agenda and then
Yeah.
we can get started?
Yeah. So,
So, hello, everyone. Welcome to this session on Future of Digital Substations. This is a collaborative webinar between UK NGN, SIGRE UK NGN, and SIGRE India NGN. So, first, there will be an introduction about SIGRE UK NGN by Maria, and then there is a introduction about SIGRE India NGN by Aditi, and then we will go into the technical presentation. Um, Over to Maria.
Yes, hi. Can you put on my slides, please? Okay, can you go to the next slide? Okay, so hi everyone, I'm Maria, and I am the events team lead for the SIDRA UK NGN. I am currently studying for a PhD at the University of Manchester. So, as a little introduction to SIDRA UK and especially the Next Generation Network, we are a professional network for students and young engineers in the power industry. And the purpose of the NGN is to engage with the SIDRA's activities and to develop knowledge, skills, and contact within the power industry. If you are in the UK and you wish to apply for an NGN membership, then you can follow the link or send an email to the address below. This membership is free for students and for the first 3 years for young professionals. And being a member allows you to participate in NGN events such as this one and get involved in other SIDRA activities such as joining working groups and attending SIDRA conferences. And furthermore, you can also become a SIDRA UK NGN committee member and help with the admin and organization. Next slide, please. So our NGN committee has a chair, vice chair, and secretary, which are elected positions for 1 or 2 years. And then we have a few teams which deal with different aspects of running this organization, such as the membership, communications, events, and technical team. And as I said, I'm part of the events team. Next slide, please. This is just a brief overview of the committee team and the companies or universities that we all work in. So you can see we are both from industry and academia. So it's quite a wide, quite a wide background for the NGN committee. Can you move on, please, to the next slide after this? Actually, I've already briefly went through this. Can you go next slide, please? So these are some pictures of our committee at the previous SIDRA Paris session in 2022. These are some presentations delivered by the NGN members. And finally, these are some of the activities we've organized for the UK NGN lately, such as training on substation fundamentals and the different webinars on topics that fall into the study area of SIGRE. So yeah, I think that's basically it. And these are our social media and LinkedIn pages to keep up to date with our next events. Thanks.
Aditi, I now welcome Aditi Garg, the chair of SIGRE India Engine, to introduce about SIGRE India Engine.
Thank you, Sarvanan. Thank you, everyone, for joining the call today. And thanks, Maria, for that introduction. I believe half of my work is already done about what NGN does. So let's get into the details about what NGN India has done so far. Going into the next slide, just few details about us. We are a small group. We were chartered in October 2023, and we have successfully created a steering committee team of 5 members, and we are all working towards making this NGN group in India successful. Currently, our membership is around 50, and we have good amount of participation in the working groups. Uh, as a part of this webinar, which you are attending right now, we are hosting webinars every month or so. And that is one way to get connected with the NGN group in India. We are also working on coming up with some technical visits that is up in the lines. But if that is something you are interested in India, please do feel free to drop a message in the chat box so that we can make that happen for a lot of you. Another thing is participating in the NGN Showcase in the Paris 2024 session. We have participation from NGN India this year. And another thing to get acquainted with NGN is working with the working groups and having your articles published in Electra. It's a journal which SIGRE has, so you can publish your technical articles in Electra as well. So these are some ways in which NGN India is working towards bringing the team in India and having their articles and their interest published worldwide. So please feel free to reach out to us in case you are interested. And just short highlights from our past events. These are some snippets from our webinars. One is from the kickoff, and then from few of the webinars we have been doing in the past, like the one which you are in right now. And that's it from the NGN India website, India side. You can also join NGN India through the LinkedIn, and we have already posted most of the recordings of our webinars we have done so far. So feel free to follow us on YouTube. And thank you everyone for joining, and looking forward to the session from Gopal and Deepa. Thank you.
Thank you, Aditi. Now it's my honor to introduce the first speaker of today, Mr. Gopal. Gopal is a lead protection and control engineer at Jacobs with over 12 years of experience in power system protection and control, including design, testing, and commissioning. Currently, he works on UK National Grid projects, overseeing protection and control design reviews. His wide career spans utility and industrial substation, focusing on protection and control and 61850 based substation automation systems. He holds a bachelor's in electrical and electronics engineering, and will be completing his MBA in power management this year. SIGRE member since 2021. He's part of the SIGRE India Engine Core Committee as the webinar and events coordinator. And he's also the member of IET and a chartered engineer with the Institution of Engineers India. And I thank Gopal for being a part of this amazing webinar. For the
Thanks, Arun.
next speaker, Miss Deepa. So Deepa is from the SIGRE UK Engine. She's a part of the whole system innovation team as SSE and transmission, working on smart, flexible grid management to optimize transmission networks and support low carbon technologies for the net zero transition. Prior to this, Deepa worked with PNDC, University of Strathclyde, a whole energy system research, test, and demonstration facility on cutting-edge innovation projects in the field of digital substations. With over 11 years of experience as an electrical engineer at Power Grid Corporation of India Limited, Deepa has expertise in construction, testing, commissioning, operations, and maintenance of 61850-based EHV substation. Her key areas of experience and research include digital substation automation, protection and control, synchrophasor-based system integrity protection schemes, power system stability, and hardware-in-loop simulation using RTDS. With that, I give the stage towards our experts for talking about the future of digital substations. Thank you.
Thank you, Saravanan. I will just start. Can you see my screen? Saravanan, can you see my screen?
Yeah, all good, Gopal.
Yeah.
Let's start.
Okay. Yeah. Yeah. Thanks, Saravanan. Welcome everyone. So in the first part, we will be having a overall look on the substation automation and its evolution, its past and present. And in part two, Deepa will be taking over the future and virtualization of substations. Yeah. So this is the agenda for the part one. So evolution of substation control and automation, different substation protocols, and history of IE61850 and its overview. Yeah. Uh, so around 1980s, most of the substations were kind of a manned substation, and the communication was existent only between the RTU and to the like control center. And the communication between the plant equipments or the relays was almost nil, and these were the days of electromechanical relays or single function static relays. So some of these stations with these kind of control may be there, uh, uh, and so these like most of the controls were hardwired, and also the controls were local. So this is the first kind of substation control system which was there around 1980s, and then in the second generation, the evolution came into the within the substation IDs, and there were development in protocols like Modbus, which led to the different communication, serial communication, especially like RS 232 and 485. And the cabling to the RTU was significantly reduced compared to the previous generation. And this generation also saw the developments of microprocessor based relays, and then also significantly communication technologies also significantly developed in this time period. But the most of the communication between within the substation, especially within the relays and relays to the controller, was were using proprietary protocols, which is restricted to the specific vendor, and these substations mainly used like a single vendor kind of products for a production and control operation. And around mid 1990s, there were further development, and this generation 3 saw a significant development when compared to the previous generation. There were introduction of gateways. You can see there is introduction of gateways, and in the previous generation, there is only a single controller which will receive the command from the control center, and this also has some hardwired controls to the relays and plant equipments. So here there is a separate function. The function between the station control and the remote control has been separated out. So this is where gateway has been introduced, and there was a separate station computer. And this period also saw implementation of a separate bay control unit. So the modern relays here were mostly multifunction relays, quite similar to the digital IEDs which we see in recent days. And there were overload of functions and various data points, due to which there was a need for a separate bay controller, which took over the interlocks and various control functionalities. And there is no clear distinction between the third generation and fourth generation. And so this may cover generally even DNP3 and 61850 protocol. Uh, so here and coming to the fourth generation, this is purely like a digital substation protocol completely based on 61850. So here The interface between the plant equipments like a CTVT circuit breaker have also been brought into the network. In third generation, the IDs way control units were only brought into the substation control network, which we call it as a station bus, and process bus was the process level was still using the hard wiring. And when coming to the fourth generation digital substation, completely digital substation, the communication was established between even the plant equipments to merging units. So this is like a completely digital substation where and the cost of copper wiring is significantly reduced, and the engineering cost and the substation footprint also considerably came down compared to the previous kind of substation control system. And getting into the comparison of substation communication protocols, like these are the most widely used different communication protocols that you might have come across. like uh, we generally call it as 101, like 60870 hyphen 5 hyphen 101. This protocol is developed by IEC and DNP3. It is being developed as a proprietary protocol by General Electric. Later, it has been adopted into a IEEE standard, and this communication is being widely used in North America and countries like Australia. And Modbus, this protocol is almost now being ruled out, and so this protocol, it is being quite commonly used in the industrial automation area nowadays, but not into substation automation. And 61850, as you know, like this it can also be called as a standard or a protocol, and this is completely TCP/IP based protocol. And so here we have a defined process and tools for 61850, which is not existent in other protocols. And we also have defined file types, which we'll be seeing it in second part. Uh, which is and there is no defined file types for the other protocols. And we'll also be having a quick look on different mediums for communication. Yeah. And so this TCP/IP is based on OSI, like 7 different OSI layers. So even coming to the DNP3, it uses like 3-layer EPA, which is compressed into a short form of 7 different layers. But coming into the 61850, it will go through all the complete layer. So here, physical layer, which is nothing but our physical medium, and MAC address will become contained in this data link layer, and the IP address will be linked into this network layer. And generally, like Ethernet switches, they will all be operating in this network layer. And coming to the next present introduction about 61850, this is a global standard which came out as a result of a collaboration between two different entities. One is like EPRI, UCA. EPRI is Electric Power Research Institute, which is based in USA, which like had a like working group for utility communication architecture. And in the Europe, parallelly, IEC was also developing standard protocol using the technical committee 57. And later, they merged their works together to form a common standard called as IEC 61850 around the period 2002 to 2004. And these are some of the parts which are quite frequently used or quoted, like a station bus, like 8-1 station bus, and 9-2 process bus. And there are also other protocols. Generally, like 62050 might be known generally for as a communication within the substation, but it can also be used as a communication between substation and control center. So yeah, this is about 61850. And So this is a like overall architecture for 16850 protocol, and we have different communication pathways or different communication messaging system within 61850. So the most commonly used, you might see like MMS, manufacturer messaging specification, and then GOOS, generic object oriented substation event, and sample values. So GOOS is like a peer-to-peer communication, information sharing between IEDs to share switch statuses between different IEDs, and MMS is a communication between the bay level devices to the SCADA. And as you see, like sample value, where which we generally see in a fully digital substation, where the analog values, the analog quantities from like voltage transformer and current transformer will be converted into a digital value, and then it will be fed into a process bus. And then other components, as you might see, like a gateway, firewall, which can also be used to monitor to protect the system when it is going to be interfaced with the network control center, which also acts as a protocol converter. And then we have clocks. Generally, for a common substation automation system, we'll be going with SNTP, like simple network time protocol. But for a substation with a process bus, for high accuracy, we'll be going with precision time protocol. This is again like an overview about different time synchronization methods. You can also see the accuracy of different time synchronization methods. So this is about IRIG-B. It has an accuracy of 10 microseconds to 1 millisecond. And the most commonly used, where we have like a station bus based 61850 is network time protocol, or SNTP. So compared to IRIG-B, SNTP have slightly lesser accuracy, but the limitation with IRIG-B lies in the cabling or the hardware kind of a limitation. But this network time protocol will be sufficient for a station bus protocol, and for goose and MMS related signaling. But when we go into the completely digital substation, PTP is a preferred protocol for a completely digital substation. And these are the communication medium, like Ethernet. It can either be copper, or it can either be fiber optic. So in fiber optic, we have like a single mode and multi-mode cable. So single mode cable will have a single signal sent, and there will be less kind of a distortion. So it can be used for long distance communication. And multi-mode cable, it can carry different modes of signals, multiple modes of signals, and this is generally preferred for communication within the substation, for substation automation kind of application. And single mode, it is generally preferred for kind of a line for protection application, for example, like line differential protection. So like one of the key advantages of using fiber optic is it is immune to like electromagnetic interference within the substation, and the bandwidth also considerably quite higher than that of the copper. And these are these other general advantages when compared to the copper. It has higher life cycle, and it is comparatively lesser in weight, and it consumes less power. And coming to the redundancy, there are two redundancy can be implemented in two different different types. One is software based redundancy and hardware based redundancy. And software based redundancy is generally existent everywhere, RSTP, rapid spanning tree protocol. And one of the disadvantages is that there is a switch over time between whenever a ring fails. There is some time delay to switch over between one network to the other network. So to overcome that, we have two hardware-based redundancy protocol. One is like parallel redundancy protocol and high availability seamless redundancy. So here, the communication is like completely duplicated, and the signals are parallelly sent in two different pathways. It will be sent in two different pathways, both in HSR and similarly in PRP. The communication like signals will be sent in two different pathways, and the failure like switch over time, whenever there is a failure in the communication medium, the switch over time is almost zero. There is no delay whenever we are switching into the other data packet. So this is generally, PRP is generally used for large scale networks, and HSR, one of the advantages with HSR is that it has a low deployment cost. Yeah. So this is about the redundancy, and I'm it's about end of the slide, and we can go with part two. Deepa.
Thanks,
Yeah.
Gopal. I'll now share my
Yes.
part of the presentation. Is my screen visible okay?
Yeah, all good, Deepa.
Thank you. So, Saran, Gopal has given us a good introduction to 61850 and digital substations. Uh, Talking about the digital transition and to the future. To achieve carbon neutrality, governments have set bold goals with some deadlines as early as 2035. And this requires a rapid pace of change. With this large scale integration of renewable and wide scale adoption of energy storage systems like battery, power generation, transmission, and distribution has become increasingly complex and sometimes less predictable. And the grid must be more flexible and consumer friendly to facilitate bidirectional flow of power while still meeting or exceeding the system reliability requirements. So the question is, how do you match this challenging combination, that is simultaneously increase or adapt to this rapid growth while also improving the reliability and robustness of our power grids. The implication is that we will see new approaches when it comes to addressing system resilience, with digital technologies playing a key role. And substations are at the heart of all of this. And digitalization of substations is one of the central steps towards transformation of energy systems. Responding to the need for automation beyond substation, 61850 edition 2 has already touched upon specification for things like wide area network communication between substations, or wide area communication between substation and control centers, or field area communication between substation and distribution feeders, even time synchronization. And these new specification enabled utilities to support automation throughout the grid. However, it can be very challenging for the utilities to develop network blueprints that will enable them to leverage the advantages of 61850 everywhere. For example, utilities might need to consider network service requirements of multiple domains, LAN, WAN, FAN, for use cases that depend on seamless end-to-end connectivity. So, utilities are making major changes as they strive to decarbonize, decentralize, and digitalize their power grids. Current substation architectures, where the technology is built on thousands of fixed function devices, is starting to become outdated and inflexible, and where vast amounts of data that is generated by the grid is not easily collected or shared across the wider landscape. Hence, utilities have started to express interest in extending virtualization architectures and even cloud computing to substations to make the grids efficient and agile. So IEC 61850 as a standard can evolve to support virtualization use cases with seamless workload to workload interconnection that even extends across the WAN and even to the utility data center. We have already seen that some typical applications in digital substations, which look for different levels of computing power or specific demands of operation system or specific time requirements or specific hardware resources. It ranges from HMIs, workstation for operators, historical databases, SCADA devices or SCADA systems, or even PQ management stations. And many substations have applications that run on separate computers, and it's becoming expensive to maintain and risky to maintain for certain cases of system reliability. And each of these applications might have its own hardware which can fail at any point. And to make the application redundant, we end up using small computers as necessary, which again needs to be maintained and replaced as per necessity. So digitalization alone is only a first step towards an efficient and reliable substation. And to exploit the full potential, we need further development towards computerization. So utilities are looking at architectures where applications such as RTUs or gateways or HMIs, SCADA systems, multiple of these applications can be integrated together uh, uh, with all hardware components from different manufacturers simplified, and all of these coming onto a single centralized server. The functions could be implemented as software applications, and in simple terms, it might have the potential of a longer life compared to the hardware executing them. And by separating these application functions from their hardware, we can create new architectures, even for protection and control systems, and new methods to design, commission, operate, and maintain them, including upgradation and end of life replacement. This means more transferability, flexibility, and a different priority level, which allows for an easy to maintain infrastructure that can host multiple applications and can adjust to specific situations. And it also enables a uniform, redundant, and easy to maintain hardware system at the center. Um, to optimize and modernize substations, utilities are looking for more intelligence at the edge, which means more processing power at the edge to handle these growing data and unlock the ability to continually analyze and act upon this overwhelming volume of information, and for certain applications with very minimal latency. And the first step to modernize this architecture is using standardized commercial off the shelf ruggedized servers and adopting software defined automation protection and control system on these servers. So different substation workloads can then be run and managed on a single platform. The aggregation of all these functions from multiple intelligent electronic devices into a single computational platform is called centralization. And in many instances, one computational platform can be used to execute multiple virtual machines where each machine can be thought of as a separate computer. And the use of the single hardware platform to host multiple virtual computational environments is called virtualization. And when we talk about this common substation platform idea, where we separate these various layers of applications, it proposes many advantages, as I already mentioned, improved life cycle maintenance complexity. And if we look at this common substation platforms, while it brings increasing life cycle flexibility compared with typical the hardware-based OT boxes which we had, it also enables standard configuration at substations, while sometimes it also gives the flexibility of doing remote upgrades. The standardization of hardware, IT and OT technologies, it all results in economies of scale that makes this use of virtualization very interesting. And the enhanced functionality of these basic substation applications, it advances the transition towards grid modernization needs. And it also simplifies compliance requirements wherever applicable. and decreasing the number of OT boxes while providing at least the same amount of reliability and performance. It offers a chance for advanced algorithms and softwares, which is not limited to prediction and distributed decision making, to be included in this edge intelligence. This simple and fail-safe hardware infrastructure with virtualized application layers spread across different levels creates a lot of added value during planning, operation, um, and even during maintenance, as well as the entire life cycle of a digital substation. While we speak about virtualization, architecture and design consideration is one of the most important aspect. Virtualization allows multiple systems to coexist on a single platform, simplifying the creation of redundant steps. Stemming from large IT data centers, virtualization creates intermediary layer between applications and physical hardware, enabling the virtual emulation of services and operating systems on a shared equipment. So if we look at the virtualization architectures, some of the main elements which we could see are the operating systems, the virtual machine monitor or the hypervisor, sometimes the container daemons to provide OS services, virtual switches or software defined networking plane, then virtual machines with operating systems for real-time applications like protection functions or non-real-time applications like, say, for example, gateways. Choosing and sizing the appropriate hardware platform is a critical aspect for virtualization, as it forms the foundation for all consideration for cost and redundancy. A hypervisor, also known as a virtual machine monitor, is the software that creates and runs virtual machines. And hypervisor allows one host computer to support multiple guest virtual machines by virtually sharing its resources, such as memory and processing, across all these virtual machines. If we look at applications, hypervisor could be basically divided into two groups basing on or depending on the needs of the respective applications. Say we have some very real-time applications which have very critical time requirements. We could choose type 1 hypervisors which are directly installed onto the hardware known as bare metal. For other applications, which we could use type 2 hypervisor, where the hypervisor function atop a host operating system situated between the hardware and the hypervisor. So choosing the right virtualization component is an important decision that we need to make during the planning stage. For example, for software-defined architectures, you can have dynamic and static configuration in parallel. A static configuration can be used for systems that contain a safety critical application where system resources, which enable system resources to be allocated at system configuration and build time, and then used in a predictable and deterministic manner at runtime. So everything depends on the specific application that we are looking at. And when we move on to architectures for digital substations, um, assessing the memory and resource needs for different application is crucial. I spoke about the network capabilities in digital substations. uh, that should inherently include support for various virtual LANs, virtual switches, and redundancy protocols like HSR or PRP, which Gopal touched upon. So, moreover, the implemented hardware must comply with standards outlined in the 61850 standard. Um, the various solution providers, they could suggest something like maybe requirements like 64 GB ECC RAM, where ECC RAM is a error correcting code RAM that has the capability to correct data corruption within the memory spaces, enhancing reliability in substation settings. We should also need to ensure that these various operating systems can efficiently use the shared infrastructure. For example, it's essential for the CPU, the graphics unit, or the input output layer to have built-in virtualization support. And some processors allow guest operating systems to have exclusive access to the specific hardware resources, such as network interfaces. And the computer platform requires NICs which are capable of performing VLAN tags and trunking. Certain 61850 applications, it necessitates, you know, the configuration of multiple VLAN configurations for transmission of goose traffic that includes specific quality of service preferences. So the NICs which we have should be capable of performing this VLAN tags and trunking. Uh, Say, for example, the Windows 10 does not support NIC teaming anymore. So if we are using NICs, it should have integrated teaming function. It should also be equipped with several independent Ethernet ports, and it is essential that the station computer should be compatible with HSR and PRP for smooth integration and functionality across the station levels. Virtual switches reduces the hardware cost by not requiring many physical Ethernet device interfaces like we needed for the previous generation of substation automation architectures, and especially in HSR PRP networks, which are built redundantly. Many intensive HSR PRP ports are eliminated due to the virtual switches and virtual capabilities we have in network layers. It's also crucial that the computing unit functions reliably in all types of environments where, say, for example, temperature fluctuates from -30 to 70 degrees, enduring high levels of electromagnetic interference, etc. And we are seeing some serious convergence of IT and OT, where previously many network operators, IT departments took on the roles of choosing hardware and software requirements, overseeing patch management, or operating communication networks. This IT-OT convergence through virtualization, we can see synergies developing between IT-OT standardization, IT-OT design, operation, maintenance, and in the full life cycle of substation automation. There could be coordination in unified standards and protocols, uh, coordination in IP address allocation for WAN integration, implementing shared infrastructure for upkeep and servicing, sometimes homogeneous technological frameworks, or even consolidating software licensing agreements and establishing integrated governance. Centralized protection and control is one place where we could see the application of virtualization. The implementation of software systems for system protection marked a notable shift, offering numerous advantages and some disadvantages as well. The core principle behind the centralized protection and control approach is to consolidate the protection and control features from several bay level units onto one central processor located in a substation. This would leave only process interface tasks to merging units at bay level. The main advantages sought after including enhanced functionality, sought after include enhanced functionality and decreased life cycle expenses. An evolutionary step in the centralized protection and control architecture and centralized protection and control architecture is to make it more hardware agnostic, thus resulting in virtualized protection and control. This means that protection application is no longer tied to a particular centralized device, but it is a software image that can be freely deployed to a versatile industrial server architecture, which can be hosted in different environments. Virtualization in PNC, the fifth generation shown in the figure, um, refers to using software to simulate the function of a conventional PNC device within a physical host, which is a ruggedized computing hardware codes, as I mentioned before, which is a commercial off-the-shelf component. The software image could provide real-time deterministic protection and control, And the replicability of this image can create several instances, which makes the whole life cycle very much easier to manage. Software images with different applications providing monitoring and diagnostics can reside on the same host machine. For example, a set of protection control and metering functions of several apparatus residing in a single software image, which can provide protection of several elements, like, say, for example, distance protection for line, transformer differential, or a set of directional overcurrent functions, all coming together in a single software image hosted in a COTS. And adopting the CPC strategy will necessitate a fundamental change in the approach to designing, producing, installing, testing, operating, and maintaining protection and control systems. Um, the IEEE K15 working group, it had published a report in 2015 on centralized protection and control, and it concluded that development of a recommended practice guideline in the use of CPC may accelerate the deployment of such systems, specifically in distribution networks. It also discussed various possible architectures of CPC, and the technologies were reported as valuable in enhancing distribution protection and automation, especially with the increase of integration of distributed energy resources. And as distribution networks evolve and grow, there are additional chances to integrate CPC systems, and experiences gained from distribution sector can guide the application of CPC in other areas within the power system. And while we highlight the benefits of virtualization and the benefits of functionalities independent of hardware, we need to be wary of requirements so that we can leverage the advantages of these functionalities independent of hardware, which means the ITOT convergence, which I already talked about, the ability to change functions on hardware devices anytime during the PACS lifecycle without affecting the core PACS application, possibility to replace the hardware which hosts the specific set of functions. So when we replace this, the PACS configuration can be kept untouched from a functional perspective, which means the new hardware might not belong to the same type, even it might be based on a different principle or a different architecture. The functions could be grouped into virtual devices. Uh, it gives, or it enables, the flexibility to communicate using open and interoperable protocols like 61850, so that function can be easily transferred between multiple virtual devices. Additionally, interchangeability might also come up, uh, wherein it allows a different software from a different origin to be executed in the same environment, given the fact that the functionality provided is similar. This free allocation of functions and provision of functions from various providers with independence from hardware, it allows implementations with different granularity, but it needs to be ensured that the chosen granularity will match our required performance and reliability requirements, like availability, time synchronization requirements, um, or those performance requirements that might be derived from 61850-5, which are specific to protection and control functions. And all the softwares need to inevitably comply with specified levels of cybersecurity requirements. And as I already said, uh, in the end, the selection and dimensioning of right hardware platform would play a major role in virtualization, and would play a major role in all the redundancy and cost considerations. Uh, Engineering is the very start of the system lifecycle. It starts with the specification phase and then moves into the commercial phase, where we request for quotation or conclude with contract signing. And in this engineering phase, we use tools like system specification tools or system engineering tools as per 61850 standards. Functional requirements and the associated performance criteria are to be documented in the basic application profiles in accordance with 61850, which is anticipated to offer formats that are machine readable. The most important phase of any project, which is the engineering phase, should provide the detailed engineering according to the project specifications. The introduction of formal system specification description, the SSD in 61850 edition 2, it paved the way to decouple application functions from physical hardware. Presently, some system configuration tools support the system specification and system configuration process in a single tool. You may utilize a system specification tool to do both. Um, the distinction between the two engineering processes is that in specification, the required application functions are denoted by logical nodes, and these are assembled into virtual IEDs. And during system configuration, logical nodes are linked to real IEDs by using the IED capability description or the ICD file. And this phase concludes with the comprehensive system description, that is the SED file, which contains all the essential details needed for information interchange within the network. Each IED requires a subset of system configuration information, which is provided by the device-specific configured IED description or the CID file, which is derived from the SED file using the IED configuration tool. To allow local modifications on the IED level and the necessary update of SCD file, we have instantiated IED description or the IED files, which are created by the ICT tools and uploaded onto the SCT. So we can have either bottom-up or top-down approach for engineering and specification. It's important to recognize that these processes generally manage the configurations pertaining to information flow, and it's not usually the functional behavior. The setting function is not part of this. It's not uh, part of the process that we explained. Setting function is part of the ICT. As previously stated, where these processes operate separately from the hardware, the implementation of these protection and control functions with function independent of hardware will obviously necessitate extra engineering efforts, but simplified ones. The next key milestone would be testing. And in testing, factory acceptance test is the first and key milestone, which consists of several validation steps at the factory. And once we successfully execute the factory acceptance test, the system will be installed on site, and the final site acceptance test provides the validation of system functionality with various set of tools. 61850 provides ample guidelines to entire quality processes, including recommendations for functional testing and requirements for conformance testing. And these guidelines are anyway independent from hardware and therefore applicable to protection and control functions, control systems with functionalities independent of hardware. For example, 61850 specifies requirements regarding the engineering tool support based on use cases along the entire life cycle. It specifies system-related function test principles, um, which had been added to parts like 10-3. Furthermore, there are additional 61850 series parts which provide requirements regarding system management during the life cycle of the protection and control systems. Keeping all this in mind, performance test of the host hardware and the execution environment, it's key in the testing of PACS, virtualized PACS systems. Benchmarking of host to evaluate performance parameters like computing performance, memory bandwidth, memory capacity, input output workload, or network bandwidth provided by the host machine, its execution environment, including operating system. All these are key things that needs to be considered. For example, the time it takes to switch the context between multiple protection and control virtual machines after running them on the host machine, it greatly affects the operational performance. So it's necessary to evaluate the number of PACS virtual machines that can be run on the host machine simultaneously. To ensure that these virtual machines run with the given performance specifications, even under extreme conditions, the resources must provide a certain performance margin. So we can see that the impact of this centralization and virtualization concept is significant during commissioning testing. The digital aspect enables conducting commissioning testing in a lab or an office setting, while we can do only the IO devices based or physical parts based testing at site. It is desirable to perform the final commissioning checks at site so that we have a complete test of the entire system at site, while we can also leverage the capabilities provided by virtualization by testing majority of the aspects in a lab based setup or an office based setup. It's pertinent to recall that a CPC-based substation protection and automation and control system (ISAS), a pilot project was in operation in Russia in 2015. To conclude, the digital transformation has urged grid operators into upgrading their distributed automation systems to support novel smart grid applications and to leverage the flexibility offered by the virtualization of systems. Concurrently, the digital grid became more susceptible to external dangers. Obviously, the growing frequency of cyber attacks or IT related dangers that we must be wary of even from the designing and planning phase. In the new context, the PACS virtualized or centralized PACS architectures necessarily have to be configured more regularly to adapt with the changing settings of functions, or more regular updates or upgrades, sometimes even the entire software. The hardware and software abstraction of PACS allows to perform these upgrades in an interoperable way, independent from vendor specific tools. Currently, several standardization bodies are addressing these architectures, including IEC, IEEE, SIGRE, etc. And 61850 will be necessary to address data model expansions, engineering procedures, and file formats, uh, which makes these standardization and these activities more easier. Concurrently, the IEEE PSRC H45 working group had spent great efforts on the PEC 37.300 to focus more on performance benchmark and assessments. The key challenge in transitioning to a software dominated PAC system will be automating the entire digital lifecycle management, and the concept of system orchestration is at the heart of this. Besides standardization activities, we have proof of concepts and pilot installations, which will provide the base for further innovations and further business opportunities. Innovations like app stores for PSC softwares, intelligent test tools, or PSC as a service solutions all are in progress at different stages. And we need to adopt lessons from these projects. And knowledge management is at the foundation of all these so that we can accelerate the adoptability of these evolving technologies and evolving functions. Thank you.
Thank you, Deepa. I think that was a very informative session. Um, now, if Gopal and Deepa, can we just answer some of the questions? So I'm just going from the bottom, the recent questions. So one of the questions was, can we integrate directly third-party equipment like PDMS, DGA, etc., which work on protocols like RS-485?
So when we say virtualization, the intention is to allow integration of multiple open protocols and multiple equipments that work on standard protocols. I cannot comment specifically on a certain equipment or a certain protocol. I have worked on 61850 standard extensively, where we have leveraged the capability of 61850 to enable virtualization.
Okay, thank you for that. Another question was, can you please throw light on combined configuration file in digital substation for protection setting file and IC 61850 communication configuration file? Is
Could you please elaborate more on the question?
I hope the person who typed up the question, if you can go a bit more detail in the question while we go to the next one. So, taking up another question, what is the mode of communication channel between main and remote end substations? PSC, MPLS, direct fiber, etc.
I have worked on direct connections using direct fiber as well as MPLS.
Okay,
Again, it depends on the type of application you are looking at
got it, got
and
it,
its specific requirements.
got it, got it. Thank you. Uh, can we introduce an operator environment along with the engineering environment?
Uh, what would be the requirement here to combine an operator environment and engineering environment? So if we are speaking about a virtualized system, yes, we can have an operator environment and an engineering environment on the same hardware, if that's the question.
Okay, got it. Thank you for that. Are there any limitations with hypervisor?
Um, Obviously, every architecture would have its own pros and cons. As I mentioned, we can use hypervisor architectures or we can use containers for virtual machines. Everything again comes back to what is the application you are looking at. If it's an application that has real-time requirements, you would choose a specific architecture. And if it has non-real-time requirements, you would look into a different architecture. If we speak about digital substations, solutions, there are umpteen number of solutions available to your problems. So the question is to essentially understand what is your problem, what are your requirements, and to design your architecture against your requirements rather than, say, for example, if a solution A uses artificial intelligence to tackle a certain problem, it's not necessary that a certain another problem should also use artificial intelligence to solve that problem, because artificial intelligence is something, it's a very cutting edge, or it's very novel. It comes back to the question, what is your problem, what are the requirements, and design the architecture and the solution against those problems rather than using those cutting edge theories or solutions for as a bracket.
That was a beautiful answer. Thank you for that. Um, PRP, as shown, there was end-to-end hardware redundancies. Then why there is discussion on switchover and its time? So if either of you can answer that. Why are we talking about switchover and the switchover time in case of PRP if there is end-to-end hardware redundancy? I guess that was the question.
Okay, like switchover time has been compared against RSTP.
Okay.
Yeah, it has been
Okay.
compared against RSTP. RSTP is also a redundancy protocol, but it is a software based. So to in comparison to that, like PRP has zero switchover time. So it has been compared against RSTP.
Okay. Thank you. Does double star configuration give rise to interface issue and with goose communication? Is there any interfacing issues because of double star configuration?
Double star, the sense like two PRP rings. I'm not
Yeah,
sure,
it was not
but
clear in the question. Yeah,
okay,
but
okay. But like there are devices, in order to connect non-PRP devices into PRP ring, like a redundancy box or red box. They call it as a red box.
okay.
Yeah.
Okay.
So
Thank you. Uh, Another question. Are we not introducing any additional delay for closing and tripping signals from control center by using merging units, MUs? Can you comment on, are we introducing any time delays because of using merging units?
no, certainly not. Yeah. So since it is going to be the signals are going to be time stamped and uh, using PTP, and then the signals, critical signals can be prioritized using a like virtual network.
Got it.
So that will
Got
not
it.
delay the critical signals like trip commands.
Got it. Got it. Thank you for that. And I have a quick question to, ask for Deepa. Can you comment a bit on cybersecurity when it comes to virtualization, and how will it be different from what the, products are available now?
So I'm not a cybersecurity expert, but then from my previous experience seeing how they engineer the cybersecurity solutions, I understand there is capability of virtualizing the security aspects within the switch. So
Okay.
previously, where we used to define firewalls, there is a capability to virtualize all these functions within the switch environment itself.
Okay.
But
Got it.
again, as I said, I'm not a cybersecurity expert, so apologies if I'm not very clear on. Uh,
Thank you.
yeah,
Thank you for that. Thank
yes.
you for that. Okay, so I guess that we have crossed our time limit for that. Participants, if you have any questions, please drop a mail. We will be sending you directly the details of the webinar, and the webinar recording will be posted on YouTube as well. So please do not worry about sharing. So we will be posting the complete recording in webinars, and you can always get in touch with us if you have any questions for our experts. So with that, I thank both Gopal and Deepa for their time and for the effort that they have given for this. And I hope the participants found it very interesting. And we hope to see more webinars in collaboration and from Sigre NGN. And we'll be sending you a feedback shortly. So in case of any comments or opinions, please do share with us. And let's go forward as a community. Thank you so much. Thank you, Deepa. Thank you,
Thank
Gopal.
you very much for the opportunity.
Thanks,
Thanks,
everyone.
everyone.
Thanks,
Thank
Deepa.
you.
Thanks, everyone.
Thank you, Gopal.